Recording in progress.
Yeah, cams on everyone. Let's start off. So last thing that we did was optical cable. Now after this we have, why is this not? Yeah. Okay. Let's go ahead. Are the cams on? So after this, we also have something, the based on prisms, but I think that we will do in the end, because in prisms there is a part called dispersion, which is not there for advanced, but it is only there for mains. So we will do that whole thing at the end. So great. So next thing, refraction on curved surface. I'll also send you some small theory on, this rainbows and all that stuff. You can just read it. There's some theoretical things just to get a little idea, because CET may sometimes do ask, in a rainbow, how are the colors formed? Is it violet to red or red to violet? And they do ask little weird ones. But they do ask. Again, like I said, we are not going to do any derivations. We are going to put the result directly. Others, put your cams on. So let's say we have mu1, we have mu2, and this is the radius for curvature r. So it's a curved surface. So left and right side, the medium is different. So object, light rays would hit the surface. They might meet here. So the formula for this is mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. That's the relation between the object and the image distance. Now, like I said, we don't worry about the derivation part. If this curve becomes a straight line, then what becomes r? R becomes infinity, isn't it? The radius of curvature of an infinite line or a straight line is infinity. That means this right side term will become 0. Then this will become apparent depth ka formula, if you see. So the radius on a curved surface, if you make r infinity, it becomes an apparent depth. The magnification m is given by mu1 v by mu2 u. So here you have to be careful exactly what is mu1 and what is mu2. Don't say object and image. Say like this thing. This is the medium of incident rays. When light rays fall on the interface, the region from where the rays are coming, that is mu1. Mu2 is the medium of refracted rays. That's a better terminology. Actually, when we did this thing, right, you could have done the same thing for this logic also. When we did this apparent depth, there I wrote here incident and refracted. So like that's a better way. Instead of saying object and image, because sometimes the object will be virtual object, then what will you do? Again, same story. U, V, R must be taken with sign convention. Note down these formulas. You need these two. It is the same sign convention we followed in mirrors. Right? This is valid for paraxial rays, and object should be on the principal axis. If the object is not on the principal axis, you know what to do. Drop the foot of the perpendicular, find the image, and then use magnification and get the image. Okay, let's put on those formulas and then let's see. Yeah, do keep your cams on or else I'll start removing you from the classroom. All copied. Great. So let's see some questions so that you get used to it. Three by two. This is two. The radius of curvature is 20 centimeters. This is the object at 40 centimeters. Find the position of the image. The object is at a height of 1 centimeter. It's a 2 centimeters. Find the position of the images. All distances are measured from the pole. You can that's your formula, that mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. And that's your magnification, minus mu1 v by mu2 u, which is height of the image by height of the object. Minus 20 indicates what it is, virtual. The image is forming on the left hand side. So the rays have actually got diverged after crossing the medium. Right, Samyak. Right, Trishi. You got an answer? You can type in the chat box here to the co-host. नहीं हर्षिता, minus 20 है, but check करो calculations. Be careful with the signs. Like I keep saying, the whole thing is about sign convention and the formula. If you are comfortable with these two, that takes care of 60-70% of the chapter. And then the other standard results and all that stuff. So let me show you the first one. Let's see whether you got the signs right. So light rays are going to the right. So right is positive, left is negative. So I will write the values here. So light rays are going from left to right. So what is mu1? Mu1 is 2 because that is the incident medium. What is mu2? 3 by 2. So if you're confused, write it down, at least for a few questions till you get used to it. What is u? Minus 40. What is radius of curvature? Plus 20. Why? If you extend this, the center will be on the right hand side. It is on the positive axis. So r is positive. Apply the formula. Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Substitute here, 3 by 2 v minus mu1 is 2 by minus 40. Mu2 minus mu1, that's 3 by 2 minus 2, r is 20. That's 3 by 2 v, 1 by 20, and that's minus 1 by 40. Yeah, that's 3 by 2v minus 1 by 20. I'm getting 30. I goofed up somewhere. Mu2 is 3 by 2, mu1 is this. 2 by 40 is 1 by 20. This is minus 1 by 20. That will be minus 3 by 40. So V is equal to minus 20 centimeters. Meaning what happened exactly? The light rays went here. Then they became something like this. So when you extend them backward, this is where the light rays are coming from. I mean, that's what an observer on the right side will think. 20 centimeters. So this is a virtual image. That is how you decide whether something is virtual or real. If they're meeting on the right side, then they would have converged. So if you're getting image on the left side, the writers have diverged. Are you clear with this? The ray diagram is always important. That will give you an understanding what is happening. All clear with this? What about the second one? Second one here is the question. Try, I'll give you a minute more. This time you even have magnification. Let's see. So when the object is not on the principal axis, step one, drop a perpendicular. We'll get O dash, a shadow. So let's find the image for O dash. What is mu1, 3 by 2? What is mu2, 4 by 3? The refracted rays. What is u, minus 20? Lighters are going from left to right. What is radius of curvature? Plus 20. Apply the formula mu2, 4 by 3 by v minus mu2, 3 by 2 by u. Mu2 minus mu1, 4 by 3 minus 3 by 2 by 20. This doesn't look great. Minus 3 by 40. That is 8, 8 minus 9 minus 1 by 6 minus 1 by 120. Minus 1 by 120 minus 3 by 40. Multiply 3 and 3. That will be 9 minus 10 by 120 minus 1 by 12. That is 3, 4. V is equal to minus 16 centimeters. Did I get it right? Check. Like, I don't know. I don't think it is wrong, but I'm not sure. See if I'm wrong. See where the calculations went. That's what I'm saying. If you just keep these things properly, it's just a matter of calculations. And then the magnification formula is minus mu1 v by mu2 into u. So mu1 is 3 by 2, mu2 is 4 by 3, v is minus 16, and u is minus 20. So the 3 will go up. We'll get minus 9 by 8, 16 by 20. This is 8, 2, that is 10. So minus 9 by 10. Magnification is that. So height is 2. So height of the image by height of the object was minus 9 by. So height of the image will be minus 9 by 5 centimeters. Minus indicates it got inverted. So this image is forming 16 centimeters somewhere here and inverted somewhere here, I dash. And the height is 9 by 5. And this distance is 16 centimeters. So I think, yeah. Paramuma forgot to multiply with 2, but yeah, I think this looks right. Check your calculations. All clear with this? Straightforward question. Matlab, you do get these kind of questions, it means. Not tough, but you have to be careful with your signs and the calculations. All clear with this? Next one. We have a glass sphere. Mu is equal to 2. Outside is 1. The radius is r. And this right side is silvered. Basically, it has become a mirror on the right hand side. That so we have a refraction and a reflection. And you placed an object O at a distance of r. R is the same thing, the radius. Find the final image. So when you see a question, first thing you should always ask how many phenomena are happening. So lighters will go here, refraction, hit the mirror, reflection, they'll come back, refraction, then they go out. So refraction, reflection, refraction. So you have to do 3 different problems. Get it? Nothing to think, brute force. Apply the formula, keep solving. TIR, paraxial rays, they'll always enter almost at an angles of 0. So there'll be no TIR. Right, Arya? The formulas, whatever we are deriving, all are valid for paraxial rays. So there is no TAR possibility in this scenario. Everyone should give it a try. Anyone confused with the sign convention or the formula, please ask. Clear, na, Tanishka? Tanishka, formula is clear? Let's go ahead. Pratyasha? Clear? Advai? Solve. Give me some answers then. Devanshi? Clear so far? Right, Aditi. We have one answer. नहीं सम्यक. You didn't complete it. एक और refraction आता है ना? You got the answer. This is after reflection. You forgot there'll be one more refraction after this. So first you have to apply refraction. That will be the image for the mirror. Then you get reflection. That will be the object for the refraction again. So refraction, reflection, refraction. Total 3 times you have to apply the formula, but I did give good numbers. It looks scary, but when you start solving, they do come out to be decent. नहीं परम. Right, Harshita. So when you guys say minus, right? Exactly what minus, right, Anvita? Right, Harshita. From where? So report the answer that way. From the mirror, right side, left side. Because the sign convention has changed, right? Writers have turned back. So plus and minus का sign meaning change हो जाएगा. Let's see. First thing, let's do the refraction. So this is the object. Outside is 1, inside is 2. Letters are going from left to right. Mu1 is 1, mu2 is 2, u is minus r, radius of curvature r is plus r. Because for this interface, r is on the right side. Apply the formula. So mu2, 2 by V minus mu1, 1 by minus R, mu2 minus mu1, 2 minus 1 by minus R plus R. When you do this, interestingly, you'll get 2V is equal to 0. This is where people get stumped, like what the hell does it mean? This means V has become infinity. This means these rays are parallel. That's the meaning of infinity. So what is image? Image is the point where the light rays meet. And you're getting infinity, means the light rays are meeting at infinity. Which light rays meet at infinity? Parallel rays, isn't it? Two parallel lines meet at infinity. That means these light rays, after hitting this, have become parallel. That's the meaning of it. That's why this becomes easy after this. Now the mirror will think light rays are coming parallel. Now we do for the mirror. So the mirror will think light rays are coming parallel. And we know what happens when a parallel light rays come. They go and meet at the focus. That would be your second image, I2. And this distance will be R by 2. Now these light rays will again go back. Now we have second refraction. So mirror right there, it saves you one step. So now again, this interface on the left-hand side. So refraction is happening again on this surface only. So this would be the object I2. This distance will be 3R by 2. Light rays are going from left to right. So left is positive. Sign convention. So U is minus 3R by 2. Remember, we always follow the light rays. So left side is positive now. Mu1 is that medium from where the light rays are coming. So light rays are coming from 2 and they're going out to 1. So mu1 is 2 and mu2 is 1. And the radius of curvature is minus R because the center is on the right hand side, but the rays are going to the left hand side. Apply the formula, you get 1 by V minus 1 by mu2, right? Mu2 is 1 by V, mu1 is 2 by minus 3R by 2 is equal to mu2 minus mu1, 1 minus 2 by minus R. I think I scribbled it too much. How much is this? So 1 by V plus 4 by 3R, and that's 1 by R. Send it that side, we get minus 1 by 3R. So V is equal to minus 3R. Minus 3R meaning these rays have become something like this. And when you extend them backward, they're meeting here, I3. So again, from where 3R? 3R from here. Because all distance are measured from this pole. So it is R on the other side of the mirror, isn't it? Other side of the thing. So this is at a distance R. So it depends on the option, how they give. It is on the right side of the mirror at a distance R. All clear with the steps? There. So reflection, refraction, reflection, and refraction. If you say there is nothing new, like the only thing is the new formula, but yeah. Image is a dot. An object will give infinite light rays. We just take 1 or 2 for convenience. So the infinite light rays coming from an object. All clear with this? I hope you can see the resemblance, like nothing new, like only the formula is different. Next one. Let's say this is mu2 and this is mu by 3 by 2. And let's say the radius of curvature is 20 centimeters. We have an object here which is going with a speed of 2 centimeters per second at a height of 1 centimeter and at a distance of I hope I don't get infinity, 20 centimeters. Find the velocity of the image. And this is the worst thing, right? Like not exactly completely worse, but yeah, this is bad. Find the velocity of the image with respect to the ground. If you start going above the principal axis, you get a y component. Yeah, you're not getting infinity at least. Let's get this. You can't use the formula we derived in mirrors. You have to derive a new formula. But before that, let's find the image of the shadow. You need that information. Try. This is lengthy. I'll give you 2, 3 minutes more. That's one thing with reoptics. The questions are manageable, but you need to keep solving. Let's find the image ka thing. So mu1. So if you drop the perpendicular here, we get the shadow. We need the shadow for data. O dash mu1 is 2, mu2 is 3 by 2, radius of curvature is plus 20, u is minus 20. Substitute in the formula 3 by 2v minus mu1, 2 by minus 20, mu2 minus mu1, that's minus half by r is 20. This is 3 by 2v, that's minus 1 by 40. That's be minus 1 by 10, multiply 4 and 4, that's minus 5 by 40, minus 1 by 8. That's 2, 4. V is equal to minus 12 centimeters. Mm, Is that clear, everyone? So this is the position of the shadow. Okay, now what? Now how do you find the velocity? If you remember the process, you have to go back to the derivation. What was the derivation again? Mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. Differentiate with respect to time. This is what we did in mirror formula, if you remember. This would be mu2 minus 1 by V square dV by dt minus 1 by mu square du by dt. RHS will be 0, so but I can write it down if you want. minus of mu2 minus mu1 by r square dr by dt. Now here the radius is not changing, but they can ask a problem like this. You know how? They will say there is a water drop and this water drop ka radius is increasing with time. So you can play a game like that. So now the r also will come into the picture. Now, here we are not doing it, but this term would be 0 because we are taking r is constant. Now if you rearrange these terms, you will end up with dv by dt is equal to mu1 by mu2 into v square by u square into du by dt. This is velocity of the image with respect to the pole. Remember, these are relative velocities. And this is in the, what do you call, x-axis. This would be mu1 by mu2 into v square by u square. Du by dt. That's the velocity of the object along the pole. These are components of velocity along the principal axis. This is not the full velocity. I know mu1 ka value, I know mu2, I know u, I know v, I know everything. Dump it there, you'll get the answer there. What about the other one? We use the magnification formula. Magnification is height of the image by height of the object, which is minus mu1 v by mu2 u. So from here we get height of the image will be minus mu1 h naught by mu2 into v by u. Differentiate this. So when you differentiate this, dhi by dt, this will give you your vertical component vy. Mu1 is constant, mu2 is constant. V by u ka differential, I'll use the product rule, 1 by u dv by dt minus 1 by u square. This would be v by u square du by dt. Yeah, it's pretty little lengthy, and this is 1 by u. And remember, this is the velocity of the image with respect to the pole, the horizontal component, and this is the velocity of the object with respect to the pole. You know this value, substitute there, and you'll end up with an answer. So you know everything. Other steps clear, everyone? So this will give you the Vx and this will give you your Vy. What's I saying? We are getting this thing as 0.96. So you guys can verify your answer. Anyone also got Vy? Okay. So your final answer would be velocity of the image with respect to the ground frame. If you substitute the values is 24 by 25 I cap plus 2 by 125 J cap. Samyak has given it. So you guys can verify the answer. At this point, it is all about substituting the formulas. Any doubts on this? This is what I said. Know the formula. Process is same. What we did in mirrors, we did the same thing. Any doubts? Anyone not clear with anything here? Please ask. And they can make this really bad. Right? They can do a lot of things. They can change the mu ka value. They can change the, a lot of things. The r ka value and all. But no matter what they change, you always have to do this part. Take the formula, differentiate. Let them do whatever they want. It doesn't matter. Don't blindly remember the formula. Clear? Next one. Any doubts on this? Right? Don't worry about the notes. I'll send you the PDF. So focus on solving and understand and absorb everything. Let's see the next one. This is an important model. You will see these kind of models a lot. You have already seen one. Let's say we have a curved surface. So we have something like this. And these are also called as thick lenses. And this side is silvered. This radius is 20 centimeters. This mu is 3 by 2. Outside is 1. This radius is 10 centimeters. Object is somewhere here. From here to here, this distance is 40 centimeters. From here to here, this pole to this pole, the distance is x. Find x if the final image falls on the object. So before starting the question, first thing, what should you ask? How many phenomena are there? How many phenomena are there? So always follow the light rays. Light rays will hit here, refraction, reflection, refraction. They should come back here. 3 phenomena. Let's see how will you approach this. Now, there is no need to actually solve the whole thing. If you understand something, you will get it pretty fast. That's what makes this really good. Take a minute. So this image forming on the object itself is a very standard and very important question. They come a lot. So interestingly, na, यहाँ पे Arya, there are 2 answers. Right, Param? So instead of going ahead with the solving, first you need to ask yourself, if the final image is forming on the object, that means the light rays have come back the same way, isn't it? That's the main idea there. If light rays have come back the same way, that means the mirror saw the image in some way, so that the light rays have retraced. So like, and that's how you ask, and then you see. Think. I'll give another 30, 40 seconds, and I'll show you. Right, Samyak. So first, let's do the first refraction. So the light rays are going from here and they hit here and they'll form an image somewhere here. So let's find that. Apply the formula mu2. Mu2 is 3 by 2 by V minus mu1. Mu1 is 1 by U. U is minus 40. It's on the left hand side. Mu2 3 by 2 minus 1 by R. R ka center is on the right side. So that is 10. So this will be 3 by 2V 1 by 40 by 1 by 20. When it goes that side, you get 1 by 40. 1 by 40, 2 will cancel 20, V is 60 centimeters. That means this image, after refraction, is forming at 60 centimeters. Now, that's it. This is the only thing you need to do. And then from here, you argue there are 2 possibilities. Case 1, this image which you are forming, if it forms at the center of the mirror, then the light rays will go back the same way. So image I forms at the center of the mirror. Then the mirror will think light rays are coming and hitting it normally. So this must be the center. If this is the center, then this distance will be 20 centimeters. And this thing we already got 60 centimeters. That means X must be 80 centimeters. So then what would happen? These light rays from here will go, hit the mirror. They will retrace the same way and then they come back. The second possibility, this is the thing most people generally forget. The image eye can also form at the pole of the mirror. Because if the object is at the pole, image also will form at the pole, remember? That's one case there. So image eye forms at the pole of the mirror. That means this is how this must have happened. So these light rays must have hit the pole. And see what happens. This is what happens. Let me draw one light ray each. So the light ray, it went up. That will hit the mirror, will bounce, and will come back this way. The light ray which went down, that will hit the pole and will come back from the top. You get it? So this happens at the pole because we know that is a normal. This is theta and this is theta. That means this distance itself is 60 centimeters. So X is 60. So this is a multiple choice question. Both are right. All clear with this? But one thing happens. If the object has a size, the image gets inverted. Isn't it? The letters on the top are going bottom, bottom letters are going up. So you get an inverted image. But it's a point, so that's okay. Any doubts on this? So that's your refraction on curved surface. So that's the main idea there. The next thing is lenses. So refraction on curved surface is a more powerful thing, right? Lenses is actually a subset of it. It's like a special case. Now in this, we will study thin lenses. If the lens is thick, you have to go back to refraction on curved surface formula again. So what is a lens? A lens is made of a transparent material. With at least one curved surface. This is your principal axis. So this thing will have two radius of curvatures. This is your biconvex lens. So both sides convex. Call it biconvex. This is concavo, concavo. Both the sides concave. So biconcavo. Left side is convex, right side is plane. So convexo plano. It all depends on how you want to read it. If you read from left side, this is a plano concavo. This thing is convexo concavo. Yeah, but in this there are some rules like we do that and all. We really don't care. Like it's not school ka stuff. So and just a shape there, right? And this point, right, is call it as optical center. We don't call it pole anymore. We call it optical center. So for mirrors, we have poles, and for this thing, we have optical center. By refraction on curved surface, you can call it pole. So how do you define a thin lens? So if your radius of curvature is R2, and if your radius of curvature is R1, the thickness of this lens, which is here T, the thickness T must be much, much less than R1, R2. Example, let's say your R1 is 20 centimeters. R2 is 10 centimeters. So the T is something like, 2 millimeters. We are talking something of that small, at least 50, 60 times smaller. Then we can say it is a thin lens. So it's always relative. clear this. Clear? Next thing. So that's one thing about a lens. So we talk about only thin lenses in this case. Next thing, what is a focus? Now, when we say focus, right, a general definition, we can use this for mirrors and everything. When you send a parallel paraxial rays, sometimes they'll ask you find the focal length of a system. So when parallel paraxial rays are incident on a system, the point where they meet or appear to meet is called the focus. So if you take a biconvex and biconcave in vacuum, these rays actually do converge. So they also call this thing as converging lens, which is not exactly true, but yeah, at a NCRT and mains level, yeah, we can say that. But later on, I'll show you. It actually depends on the mediums. So that's your focus there. And here, when you extend it backward, this is a focus. In a lens, we have 4 special light rays. If you send a parallel light ray, it passes through the focus. If you send through a focus, you will become parallel. So if you send a light ray through the focus, it becomes parallel. If you send a parallel light ray, it passes through the focus. If you send a light ray through the optical center, it goes undeviated. If you send a light ray through 2F, it will pass through 2F on the other side. Uh, there is no concept of center for a lens, but 2F kind of takes that role. So these are the 4 light rays. So whenever you want to find an image, we take any 2 of them, and the point where they meet is the light ray. Have a look at this light rays. Then let's see the ray diagrams, which we did the same thing in mirrors. We'll do it again. Have a look at these pictures. Did you guys do something like this in school for lenses also? This is for a convex lens. So if light rays are parallel, they'll meet at the focus. Images at focus, real, inverted, and highly diminished. If the object is beyond 2F, the image is inverted, real, and diminished. You should remember these things. So exactly same way we have theoretical questions in spherical mirrors, we also have theoretical questions here. Have a look at this page. Then if the object is at 2F, we get the image at 2F, real, inverted, and same size. There's no concept of center here. If the object is between 2F and F, the image will be beyond 2F and inverted, and it would be like real. Image forms after 2f. Real, inverted, and magnified. But the difference between a mirror, right, concave mirror and this, in the concave mirror, image is forming on the left-hand side, the same side. Here, the image is forming on the other side. When the object is at the focus, image will form at infinity. When the object is between focus and the pole, optical center, image will be virtual. So this gives you the vibes of a concave mirror. All clear with this? Now, using this logic, let's see a small question on this. Same question which I asked for there. So let's say if you have a lens, and let's say we have an object going with speed u parallel to the principal axis. Draw the path of the image. And let's say this is 2f and this is f. And you kept a box here. Draw the path of the image and draw the image of the box. Now, if you don't know those pictures which we discussed, then you'll have a problem. These kind of questions you can't solve with formulas. How do we do this? Remember, we draw arrows. If you guys remember this question. Similar question, isn't it? So instead of solving this, ask like this. So let's say we have an object at infinity. So this is arrow 1. Then we have, this is at infinity, and we have one arrow between infinity and 2f. So all the arrows are same height. So the head of these arrows is the path of the object. When you have at 2f, between 2f and f, just before the focus, just after the focus, between them, and yeah, pretty close to the optical center. So 3, 4, 5, 6, 7, 8 arrows. So draw the image for this 8 arrows. and join their heads. That must be the path of the image. What kind of shape will we get, Utsav, with the box? Will it be a rectangle, quadrilateral, parallelogram? What exactly? So let's draw the images. So for box one, where is the image? The image will be, if you're at infinity, the image will form at the focus. So the one ka image will form at the focus. It will be a point, diminished. For object two, the image will be between focus and pole, inverted and diminished. So it will be little small. 3 will be exactly at the 2f, same size. 4 will be beyond 2f, magnified. 5 will be at infinity. 6 is at the focus, but it is between focus and pole. So 6 will be somewhere here. 7 will be somewhere here. 8 will be the same height. That's how the images will be. Now, if you join them, there, that's how image will go. It will just blow off like pretty fast. The curve just, even that rate of change also will be very high. And here the image will be like, so that 7 would be somewhat like this. So this is how the path will look like. And how will the box look like? You kept the box somewhere here, right? So the box will be between the 4 and 5, something like this. This is how the box will look like. It will not be a trapezium, it will be a curve here. I don't know what shape is this. Yeah, that is how the box will look like. And inverted, pretty big size. Height also has increased. So yeah, that's how it looks. If they did ask you find the area of the box, you will die. All clear with this? Now, these kind of questions you can't do with formulas. You should know how the image forms at different places at different positions. You do get these kind of theoretical questions. They're not difficult, but you have to think. Any doubts on this thing? How we did this? So instead of drawing that thing, I'm saying just take 8 arrows. The head of the arrows will be the object ka position. If you draw their images, the head of the images will be the object, image ka this thing. All clear with this? Then if you go for biconcave, just like convex mirror, we have only 2 cases here. If you send parallel rays, they will diverge. So image forms at the focus. So object at infinity, image at focus, virtual, erect, highly diminished. If you put an object in front of it, so assume one light ray is going through the optical center, and let's say one light ray is going straight. So it would go like this. So when you extend this backward, that is how the image will look like. Image is diminished, erect, and virtual. So parallel light ray and a light ray through the optical center. There's only 2 cases. And this thing looks like, the convex mirror. Clear with this stuff? And if you remember the graphs, which we drew for VU graphs, those are pretty deadly, but there we already have the graph for this. So same story. You can see this is how the graphs would look like. This is a graph between V and U. That's for biconvex, and this is for biconcave. Same data, like, you have to put it as 2f and f and everything. So I did send you this, I guess, but so that's your biconvex lens. There, can you see how they're meeting? So the one in the middle, right? That's your ray, which is the going to the principal axis that's going straight, and the other two are parallel. They do meet at the focus. There, this is the biconcave. And if you replace back the ray, this point where the ray goes. That's how it would look. This is a convex lens. Remember we saw for mirror, similar experiment. Focal length 20 centimeters. Did you see the word there, size karke? That is actually aperture ka radius. That's where the light is enter from. That's the aperture. There, that is your holder. Convex lens. That's a screen. Candle is our object. So there, he has already marked the points on the paper, F1, F2. So there, that's your whole setup there. 2F, F, F2, 2F2. So he's calling F1, F2, but yeah. That's the top view. You light the candle. So the candle is the image. Object is very far, infinity. You kept it really far. Let us go through that, and there you get an image. Object is beyond to F1. You can see the image there. See, inverted. So you need to keep it at that position. Huh? See, if you don't keep it at the position, it will be a blur. See, it doesn't look like a candle, but see when he moves, what happens? See, now it looks like a candle sharp. You have kept it exact at that position, like it focused. There, if you switch off the light, you can see image is erect, sorry, inverted, diminished. It is real. You can actually put it on a screen. That's what happens. So if you don't keep the screen at the exact position, you will see a blur like this. What you're seeing right now is a blur. It's not clear. The same thing happens to people with glasses. If you remove your glasses and see something, this is how we see things. Object is at 2f, image will be at 2f. Same size, inverted, real. Object is between 2f and f. So you have to move it. And now you see it again. Object is beyond 2f, inverted, enlarged. Object is at focus, image is pretty large. Inverted. There you can see it's a pretty big one. And you keep it between focus and the optical center. You should see nothing on the other side except some light. So that's just some reflector like kind of thing. There's no image there. The image is inside the thing. So if you see from the other side, you can see there's a candle inside. See, you can't capture this on a screen, but if you see through the lens, you can see it on the other side. So your eyes will think there is an image inside the lens. And this is how it looks: erect, magnified, and enlarged. This is the same thing which I just showed you with pictures there, and that's how it looks. So I think this is the same thing, I guess. Uh, Same stuff. So this is an experiment. I'll show you later. We have it. All clear with this? Yeah, that's the image formation and stuff there. Take a break. Come back by 9:45. We'll continue from here. Then next we will derive the lens maker formula. So any doubts so far? Anything that you're not clear, please ask. ठीक है, take a break. Come back by 9:45. We'll continue from here. Yeah, cams on everyone. Let's start off. The next thing is Lensmaker formula. This derivation is important. I think in this entire thing, this is one formula we are going to derive uh, because in this there are variations. If something changes, you need to go back to this derivation. Others cams on. So what is the idea here? So a lens is nothing but two refractions basically. So let me take a little big one. So let this radius be R1, let this radius be R2, let this be mu lens, and outside it be mu medium and mu medium. And let the distance between them be some t. So let's say this is your object and this is where the first refraction happens. So light rays will go here, hit this surface, and then they will try to meet somewhere here. But even before meeting, the light rays will get blocked by R2. So I1 becomes your virtual object. So for the first refraction, apply the formula. So we will, this is the pole here. So here the object distance U will be minus OP, right? And the image distance will be P to Y. So actually should measure all the distances from here. So this is P1, this is P2. Yeah, that was the thing. Now when you apply the formula, this would be mu2 by V minus mu1 by the distance will be OP1. We will put the sign later on, is equal to mu lens. So let me write this thing also. This is mu medium and this is mu L. So this is mu lens minus mu medium by R1. So don't worry about the signs for now. We will put the sign convention later on. This is equation 1. Now, when you apply the formula for the second thing, these lighters are supposed to meet at R1. So then they would go somewhere here and they would meet somewhere here. So this is your final image I2. For the second refraction, so this is your V1. I think let me write that also in terms of this distance, P1, I1. Now, when you apply for the second refraction, this would be mu medium. Lighters are going from the medium is the second medium, mu m, and the image will form at P2, I2 minus mu incident, that is your mu lens. The distance is measured from P2, I1 is equal to mu medium minus mu L by R2. There. So this is how it would look. So the distance are measured from the pole, right? And P1, P2 ka distance is T. So now when you look at this, P1, I1 is nothing but P2, I1 plus T. So technically, this is the formula you should write, mu m, P2, I2 minus mu L, P2, I1 will be P2, P2, I1 will be P1, I1 minus T is equal to mu medium minus mu L by R2. So if you add them, nothing happens. But if your T is very, very small, if lens is thin, then T tends to 0. Then your equation 2 will become P1 I1 and P1 I1. So then your new equations will look like this. You will P1 I1 by mu m by P1 mu m by OP1. This is mu m by P2 by 2. This will become mu L. This is your equation 1, and this will become P1 I1 again. This would be mu m minus mu L by R2. Now, if you add them, this guy and this guy will cancel. and you end up with mu m 1 by p2 I2. That's your final image. Now here p1, p2 ka distance also will become negligible. Mu m also becomes OP1. This becomes mu L minus mu m 1 by R1 by 1 by R2. This is your object distance. So basically P1, P2 and the optical center all are at the same place if T is very small. This is your image distance. So if I try to write it back in our general convention, the formula becomes 1 by V minus 1 by Vu is equal to mu lens by mu medium minus 1 into 1 by R1 minus 1 by R2. This is the formula that we get. So the main idea was this: if the lens is thick, see, end of the day, what you're doing is refraction on curved surface only. So only if you make that distance between the P1 and P2 negligible, suddenly you got a lens formula. Have a look at the derivation, what we did. Clear, everyone? Remember this derivation. And I'll show you later on why you need it. You really need it. You get really good advanced questions on this. You mess up the derivation. You make the lens thick. You change the medium on both the sides. So the final formula is this. This can be written as, if you go back to the definition, if u tends to infinity, then v will tend to focal length. So this will become 1 by v. This will become 1 by focal length minus 1 by infinity is mu lens by mu medium minus 1 by 1 by R1 minus 1 by R2. That means the whole thing on the right hand side is actually a focal length ka formula. There, these are the final formulas you need to remember. 1 by v minus 1 by u is equal to 1 by f. It gives you the same feeling as the mirror ka formula. There is a minus sign in the middle. That is the only thing you have to be careful. And what is 1 by focal length ka formula? This is different from the mirrors. Mirrors made it was easy, r by 2. But this is mu lens minus 1, mu medium by 1 by R1 minus 1 by R2. The magnification is given by V by U. There, please note down these three formulas. So, new set of formulas, the process is the same. These formulas are valid for thin lenses. Lens is thick, go back to the refraction on curved surface. There is no way out. Second thing, medium must be same on both the sides. If you see the derivation, we took mu m on the same thing. That is the reason we got mu m common here. If mu m is not same, don't use the formula. Go back to refraction on curved surface. And getting it, nothing works. You always go back to refraction on curved surface. That's actually a more powerful formula than lenses. U, V, R must be taken with sign convention. And object must be on the principal axis. So all that thing is same. If object is not on the principal axis, you know what to do. Copy down these formulas. So let's get used to the formulas a bit, and then we'll see problems on this. So lenses is important. All clear with this? Copied? Now here, this is one thing you have to be careful. Suppose if you take a biconvex lens, mu m, and mu L. If you look at the 1 by focal length formula, mu L by mu m minus 1. This is 1 by r1 by 1 by r2. If your mu lens is greater than mu medium, so in this thing, if you see, right, r1, r2, that sign will be positive. The focal length is greater than 0. That means if outside the lens ka medium is greater than the surrounding medium, the light rays actually converge. This is a converging lens. Now, for some reason, right, the CET people always think it is converging, but you can mess up. If your mu lens is actually less than mu medium, suddenly this whole thing becomes a negative sign. That means the same lens. Now, if you try to send a light rays, instead of converging, it actually diverges. So if someone says, right, biconcave lens is converging lens, it is not true. It depends on the medium. So now suddenly this becomes a diverging lens. But unfortunately, if you get this in CET, write it as a converging lens. That's the headache. Mains may we can argue and fight back, but CET may people will they simply say it in the textbook. The same argument we can do it for the other one, biconcave. If mu L is greater than mu M, the focal length is negative. So if you send a parallel light rays, it goes down. So think of it. Next time when you are in a pool, right? The reason why you can't see things clearly is because of this. Your eyes are designed to see things when there is an air outside. Once you go into the water and open your eyes, there is a water there. So the focal length of your eyeball has changed. So you start seeing things a little differently. You might think like, oh, I'm putting goggles, so there will be air. But after the goggles, the air, the light is still enter the water, right? So there is a refraction between the goggles and the water there. If mu L is less than mu medium, the focal length becomes positive. This will be a good, like, a multiple choice question or something. They'll give you different values of mu L and mu M, and they'll ask you converging or diverging. So blindly don't remember that convex lens will always converge. It depends on the medium. Clear with this? That's one thing. Be careful with that. Any doubt so far? Great. Let's see a few questions on this. So thin lens, if I don't mention anything, it is thin lens. R2, 20 centimeters. R1, 10 centimeters. Mu lens, 3 by 2. Mu medium is 4 by 3. Mu medium is 4 by 3. Object is here above the principal axis at a height of 2 centimeters. Let's say this distance is 20 centimeters. Let's make it up 30 centimeters. Make it even better, 40 centimeters. Get the image. First find the focal length, then apply the lens formula, then apply the magnification formula. So the process is exactly the same as mirror. The formulas have changed. Mirror mein your life was easy. Focal length was R by 2. Here, focal length itself had another formula. Get it? Like I said, brute force. There is really very little to think. Any answers? Numbers are bad. 160 by 3, it seems. So we got 160, we got 160 by 3. Someone is having net issues. Okay. Then we have two 160 by 3s. We have two 160s and two 160 by 3s. We have three 160 by 3s and two 160s. Someone type 160 balance हो जाएगा. So in one of the group definitely did same kind of mistakes. So yeah, three 160s and three 160 by 3s. Okay, let me check. Tarika is doing. We have four 160s. Okay, 160s are gaining now. Okay, first thing, let's find the focal length. Abhi ho gaya, I'll not count anymore. We have five 160s, so I don't know. 160 by 3s, please check it out. So let's apply the formula for the focal length, 1 by f, mu lens. I'll write down the formula once, mu medium minus 1. I keep telling you, right? The headache is the sign convention. I have seen you just mess up one sign and the whole thing goes for a toss. Mu lens is 3 by 2. Mu medium is 4 by 3 minus 1. 1 by R1. Look at this. Lighters are going from left to right. The right is positive. This side is positive. So for this curvature, the center is on the right hand side. So R1 is plus. For R2, center is on the left hand side. We did this convention last time. If you should go and check it out. So this is plus 10 and R2 is minus 20. So that would be 9 by 8 minus 1. That's 1 by 8. This is 3 by 20. I think you guys got focal length. Yeah, focal length is 160 by 3. I asked you for the image. Why do you guys report focal length 160 by 3? So that's 160 by 3 is the focal length. Now apply the formula 1 by v minus 1 by u is equal to 1 by f. So 1 by v and 1 by u is minus 40 and the focal length is 3 by 160. Send it that side. That will be 3 by 160 minus 1 by 40 multiply 4 and 4. That would be minus 160. Shit, Ray, why did we get a virtual image? I wanted a real one. Okay, what to do? That v is equal to minus 160. And then once we got this, we will use the magnification formula. Magnification is v by u. There is no minus sign. Mirror का formula में minus था, यहाँ पे minus नहीं था. So v is minus 160 and u is minus 40. That's 4. It's got magnified by 4 times. So your final image was looking somewhere like this. So this thing got super magnified and super large. So object was somewhere here at a height of 2 centimeters. And this was 40 centimeters. So these light rays, this thing which has gone like this. This light ray has gone like this. When you extend it backward, this is where it met. This was your image, 8 centimeters and 160 centimeters behind its virtual. Are the steps clear, everyone? There. So find focal length, apply the formula, get the magnification. The whole story is same. The formulas are different and stick to the same convention. Let's do one more like this so that you and I are sure that you're actually comfortably applying the formula. So y convex R2 is 20 centimeters, R1 is 10 centimeters. So mu lens 3 by 2, and let's say I'll keep outside 1. The object is at a little height, 2 centimeters, and let's say this is 40 centimeters. Get the position of the image. You should get comfortable with the formulas. My most common mistake now, I keep messing up the minus sign in magnification between mirror and this thing. I get confused between should I put minus sign for mirrors or minus sign for lenses. That's one thing that worries me. So, I mean, everyone will have their own thing. So I remember that like this. Mirror ka formula is 1 by v plus 1 by u, so that will be minus. Lens mein 1 by v minus 1 by u, so that is plus. They both are opposite. So that way I remember it. Now, since you're on the starting stage, you have to be careful. Sometimes you'll use the mirror ka formula and lens ka formula and mirror. So you can goof up. What's the answer for this? Minus 10. We have one answer. Others. Minus 10. Minus 10. Minus 10. Yeah, all minus 10. So minus 10 right over here. Someone is going to washroom. Minus 10. Minus 10. So let's see. First, let's find the focal length. 1 by f. I'm writing down directly. Mu lens 3 by 2. Mu medium 1. 1 by r1. This is very hard to be careful. Look at this thing. R1 is on the negative side. R2 is also the positive side. So 1 by R1, which is minus 10, minus 1 by R2, which is positive. So you can kind of remember by concave mein, these two should be minus minus. They will always add up with a minus sign. This will be half and that would be minus 3 by 20. So your focal length is minus 40 by 3. You're supposed to get a negative focal length. Apply the formula. 1 by v minus 1 by u is 1 by f. 1 by v and u is minus 40 and this is minus 3 by 40. Send it that side. Yeah, I'll get v is equal to minus 10 and the magnification is v by u, which is minus 10 by minus 40. This is 1/4. So you have an image forming at minus 10 centimeters at a height of half centimeter. All clear with this? I hope everyone is comfortable with the formula now, the focal length and the lens formula. Any doubts on the steps, please ask me. The sign convention, the formula, anything should be very clear with these things. So till now, how many formulas you learned? Mirror mein 2 formulas, refraction on curved surface 2 formulas, apparent depth ka 1 formula. In that apparent depth, we had apparent shift ka formula, right? So then we have another 3 formulas here. So next one. So let's say we have a slab, 2 centimeters, mu is equal to 2. Then we have a lens, and then we have a convex mirror. We have the object here. This distance is 31 centimeters. This distance is x. This radius is 20 centimeters. Let's say this is 20 centimeters. This is also 20 centimeters. This is mu is equal to 2 and outside is 1. Find X if the final image is on the object. Now totally how many phenomena are there? Slab, lens, mirror, lens, slab. 5 phenomena. But I gave you numbers good. And they asked you final images on the object. So you need not actually solve all the 5. Let's get this. So there, that's how you can keep adding more and more things. Whatever you learned. Slab, lens, and a mirror. Find X. X is the distance between the lens and the pole of the mirror. Let's calculate. Array 5. Remember, there are 2 answers possible. That story is still valid here. Always have to check. There are 2 possibilities here. Harshita, you got 1. Get the other one also. Akanksha, I don't think so. I'm not sure. We have different numbers. We have a lot of 35s. We have a 15 and a 5. I'm not sure. I'll give another minute and then I'll show this thing. So just give it a try. Let's see. So first you need to find the focal length of the lens. There is no way out. Find the focal length of the first thing. What is the shift here? The apparent shift ka formula. I hope you remember the formula there. Apparent shift is T into 1 minus 1 by mu, which is 1 centimeter. So the slab will shift the image by 1 centimeter. That's why I give 31. Then 1 by focal length will be new lens 2 by 1 minus 1, 1 by R1. So that's 1 by 20 by 1 by minus 20. That's 1 by 10. So focal length is 10 centimeters. Great. So forget about the mirror for a moment. So these light rays here, so this guy has a focal length of 10 centimeters. So this would be the image shifted by 1 centimeter. So the lens will think light rays are coming from I. That's what the lens thinks. Even though The light rays are coming actually from, oh, something of this sort. Yeah, I didn't draw it properly, but you got it. Then apply the lens ka formula, 1 by V minus 1 by U. U is minus 30 and 1 by F is 1 by 10. And this would give you 1 by 10 minus 1 by 30, multiply 3 and 3, 3 by 30 minus 1, V is 15 centimeters. That means you're getting an image at a distance of 15 centimeters. So there are two possibilities again. Case one, this could be the center. And what is R given? R is 20 centimeters. So one case is not possible actually. So these light rays which are going from here, they have to go and fall at the center. That's one possibility. You kept the mirror here. This should be the center, right? But this distance itself is 20 centimeters and you got 15 centimeters. So this is not going to work. You're getting it? So that's not an answer only. So there is no answer that you cannot fall at the center. Even if you go and stick the mirror here, you will still fall short of the center, isn't it? So image cannot fall at the center. So that case is not possible. So case one, the image falling at the center cannot happen. So the only other possibility is falling at the pole. So 15 centimeters, that's the only answer. So X is 15 centimeters. So the other case, right? The image cannot form at the center of the mirror because the radius of curvature is 20 centimeters. So you won't get the second answer. Meaning, even if you do something like this, you take a lens and you stick it to the mirror. This would be the center. You will still fall short. This is what would happen even if you stick it. Is that clear, everyone? So you won't get 35. I'm not sure how you got it. Maybe you guys took it as concave mirror. So be careful with that. Any doubts on this? All clear with this? Let's see one more. Let's say we got a lens. We have an object here at rest. Let this distance be 30 centimeters. Radius is 20 centimeters. Radius is 20 centimeters. The refractive index of the lens is given by 1 plus t, t's time. So the refractive index of the lens is changing with time. Outside is air. Find the velocity of the image at t is equal to 1 second. So if the refractive index changes, the focal length changes. So the image moves, even though the object is at rest. This is a good one. There are no standard formulas for this. You have to go back to the derivation. Let's see how you do this. This is a good advanced question, like not tough, but still. Try, try. Everyone should give it a try. How did you approach minus 22.5? 2.25 or 22.5. Okay, let's see. Again, whenever they ask you the image, what to do? You go back to the formula and differentiate it. That's the only way, no matter which thing it is. Yeah, we have 222.5. So that looks right. So let's see. What is the formula for the lens? 1 by v minus 1 by u is 1 by f. Differentiate this. So minus 1 by v square dv by dt. Minus of minus will be 1 by plus u square du by dt. Minus 1 by f square df by dt. In our question, the thing is not moving. So this guy is 0. So dv by dt will be v square by f square df by dt. So let's get the focal length first of all. So 1 by focal length is mu lens by mu medium minus 1 by r1 minus 1 by r2. Mu lens is 1 plus t. Mu medium is 1. So there. And 1 by r and 1 by r2 is 1 by 20 minus 1 by 20. So this will come out to be t by 10. So 1 by focal length is t by 10. So at t is equal to 1 second, the focal length is 10. So apply the lens formula, 1 by v plus 1 by u is equal to 1 by f. So 1 by v and the u is minus 30 is 1 by 10. So that would be 1 by 10 minus 1 by 30. Multiply 3 to v is 15 centimeters. Perfect. So what else do I need? I think I got everything. I think I can actually make my life a little easy by doing this. So d by dt of 1 by f. So this is 1 by v square and 1 by f is t by 10. So that's t by dt of t by 10. There, that's even better. So v ka value is 15 square. dv by dt is your velocity of the image. And this is 1 by 10. So velocity of the image will be minus 22.5. Minus indicates it's going opposite to the light rays. Clear with the steps? So this is how you do. So it need not be always that standard thing. You can mess up things like this also. You can change the focal length. All clear with the steps? Let's see one more. Last one for the day. We got a lens. I'll give you the focal length directly now, 20 centimeters. F is given, so there's no need to calculate. We have the object here, which is going with 2 centimeters per second at a height of 2 centimeters. The lens itself is also moving with 1 centimeter per second. Everyone is moving. And the distance between them is 30 centimeters. Find the velocity of the image in the ground frame. I told you this. Whenever something moves, first stop it. Do it in the lens ka frame and then come back. Let's go. Let's finish off. Last one for the day. Param, there'll be also JCap component, remember? Why do you think I said this is the last question? If you can finish off in 2 minutes. When did you start believing I'm a good person? -11 1 point. Perfect, Utsa. You got it. You have one answer. I'll give you a minute more and then I'll start showing. Try, everyone should keep trying. You take the formula and differentiate. That'll give you only the x component. You have to take the magnification and differentiate. That'll give you the y component. Story is the same. Right, Anvita, you got it. Let's see. You didn't get the j component, Harshita. If the object is not on the principal axis, you get a j component. Keep doing. I'll start. So you'll still have another minute or two. So start with the formula. 1 by v minus 1 by u is 1 by f. Differential with respect to time. That's it. They ask you velocity. You take the formula and differentiate. Minus 1 by v square dv by dt plus 1 by u square du by dt minus 1 by f square df by dt. In this scenario, the focal length is not changing. So this guy is 0. Then we get dv by dt is v square by u square du by dt. But be careful, v and u are measured with respect to the lengths. So these are relative velocities. So the velocity of the image with respect to length is v square by u square. This is the velocity of the object with respect to the length. And these are also the horizontal components. This is not the total velocity, because you can use this formula only when the object is on the principal axis. These are horizontal components. Then when you apply the formula 1 by v and 1 by u, u was minus 30 and focal length was 20. And this would end up with 30 will go that side, 20 minus 30, 10 by 600, v is 60 centimeters. So apply the formula, velocity of the image with respect to the lens will be v square, 60 square by 30 square, into velocity of the object with respect to the lens. So it's a relative velocity. If you stop the lens, it will think you're going with 3 centimeters per second. That would be 4, and that will be plus 3 I cap. So that will be 12 I cap. This is what the lens will think. So velocity of the image with respect to the ground frame in x-axis, I'll just call it, I'll put a small subscript x. So this is only in x direction. Will be velocity of the image with respect to lens plus velocity of the lens with respect to the ground. Everything in x direction. This would be 12 I cap, and the mirror itself is going backward to minus I cap. So this is actually 11 I cap. This gives you a horizontal component. If the object was going on the principal axis, the question would have got over here. And then we use magnification is height of the image by height of the object. Here the formula is v by u. So vy is dhi by dt. That would be h naught is constant, 1 by v, 1 by u, dv by dt minus 1 by u square v dv du by dt. H naught is 2 centimeters. U is minus 30 centimeters. Signs are important. dv by dt is again, remember, this is relative velocities. This is velocity of the image with respect to the lens, and this is velocity of object with respect to the lens with the signs. So dv by dt was 12. V was 60. This is 30 ka square. This was 3. This is 3. 4s are 6, 2s are 2 by 5. That's 60, 130 will cancel. 2, that's 180 by 900, that's 1 by 5. That's minus 3 by 5. That's minus 6 by 5. This would be your J cap. So your final answer, velocity of image with respect to the ground frame is 11 I cap minus 6 by 5 J cap, or 1.2 J cap. That's your final answer. Yeah. Right, Harshita. Right over here. Most of you got it. All clear with the steps. There. Now you are a pro. Now you understood how to handle velocities when the lens moves and the object moves. Now you'll be able to handle most of the chapter, almost 70-80% of the chapter is done. But still we have some really good models on lenses. So next class, when we catch up on Thursday, we'll continue from here. We will do more of lenses. Then we'll do combination of lenses and combination of mirrors. That would be the major part, and we'll do some experiments also. And then after that, I think next week we will do prisms, and there is some mains related portion. So I think we should take another 2.5 classes. So we will finish off with this. But it's a little big chapter, but you have to start solving. I'm telling you, next week if you start, it'll be too late. So please start solving. Finish off everything in lenses, refraction, and mirrors. You can finish off this much. If you're doing HCV, I think you can finish off for 60 or 65 questions. So that's a lot. So do start doing. If you've already done, great. I'll send you a sheet in the group today. You can try that. If you have not done this before thoroughly, please do it. Pretty high weightage. Every year you do get questions in mains, bits, and advanced also. Okay, with that, we'll wrap up for the day. I'll see you guys again on Thursday. We'll continue from here. So, so any doubts, anything else, please stay back and ask. I'll feel free to leave. So take care and stay safe.